Good morning, everyone. My name is Julien. I have a working mic, and I'm the AI evangelist for EMEA at AWS. As you know, we just had a very large event in the US called reInvent, and I was there all week, last week, which means I'm very, very jet lagged. So hopefully I will still make sense, right? If not, just boo and throw stuff at me, okay? Um, Today I'm going to talk about deep learning for developers. I like to call this session deep learning for humans, but whenever I have people with PhDs in the room, they get angry. So do we have any PhDs in the room? None? Oh, now they're afraid. Okay. All right. So this is deep learning for humans then. So what are we going to cover today? Well, I'm going to give you an introduction to deep learning, and it's going to be a gentle introduction. There will be no math at all. I'm going to use your intuition and really basic concepts to explain what deep learning is and just how the hell it works, right? Then we're going to study an open source library for deep learning called Apache MXNet. And more importantly, we're going to stop looking at slides as soon as possible, and I'm going to run some demos. And I'm going to do this using Jupyter notebooks, which is a friendly way to do that. And in the process, I will introduce you to a new service that we launched literally days ago at reInvent for machine learning and deep learning called Amazon SageMaker. Pretty exciting. And of course, I'll share some links. Slides will be available on Twitter this afternoon, I guess, if I don't fall asleep. Okay. So just a few definitions before we start. Artificial intelligence is trying to build systems that show human-like behavior, systems that can talk, systems that can understand natural language, systems that can follow complex reasoning beyond explicit programming, and systems that can do prediction, right? And it's been there for 60 years, so it's not new at all. Machine learning is a subset of artificial intelligence, which is trying to teach machine to learn from data, right? So using algorithms and data sets, we're trying to learn and show predictive behavior, classification behavior, etc., right? So machines learn without being explicitly programmed. Deep learning is a subset of machine learning. It has the same goal. Let machines understand data, learn from data. But this time, deep learning focuses on complex data, data where features, variables, columns, if you want to think in database terms, where they're not visible, right? So think images, videos, speech, text, etc. Okay, so this is what deep learning is all about. And some examples, well, Amazon Alexa is based on deep learning. It's a very intuitive system to use. You talk to Alexa, and Alexa talks back at you. So it's all natural language, but of course, behind the scenes, it's all based on deep learning, right? So this is the kind of problem we solve. We also launched last year, and again, very recently, a few days ago, more services for deep learning. Services that can understand visual context, images, videos, a service to build chatbots, services that understand text, right? Automatic translation, natural language processing, understanding the context, speech to text, text to speech, okay? So all these services are super easy to use. There's just one API call away. And we try to make them as simple as possible, but behind, if you lift the cover, if you pop the hood and you look how these systems are built, obviously they're using deep learning, right? And we've got customers doing that as well. Here's just one example that I could give you many. It's a Chinese company called Too Simple. They build autonomous driving systems, and last summer they drove that truck autonomously, no driver, for 300 kilometers in the US, right? So, and this is based on MXNet as well, right? MXNet is part of the stack being used to build a model and train the truck, Okay, so here are just a very some simple examples. I don't want to say basic examples because there are complex examples, but just a few examples on what you can do with machine learning and deep learning. So let's dive in and see what deep learning is all about. Okay, so the basic construct at the core of deep learning is called the neuron. Okay, so the neuron is basically it's trying to imitate of course the neurons in our brain, and the neuron is just a mathematical construct that takes a number of inputs, right? The x values on the left. Each input is multiplied by a weight, right? Which is a floating point value. Could be positive, could be negative. And we add all of that stuff up, right? And that gives us what we call the multiply and accumulate operation, right? We take the inputs, multiply them by weights, and we get a value, okay? And we run that value through what we call an activation function. And there are many different activation functions. This is straight out of Wikipedia. You can look that stuff up. And the role of the activation function is to decide what to do with the output value from the neuron. So for example, if you look at the, let's say, the last one, which is very popular at the moment, the rectified linear unit, well, that function decides that if the output value from the neuron is negative, then we're going to set it to 0. Okay, so we're considering that this neuron has not fired, right? We don't want to propagate that value down to other layers. And if the value is positive, then we just output it. Okay, so there are many different output values, and the role of those functions here is just to introduce non-linear behavior into the network, which is a complicated way to say we have to make a decision, right? We have to make a decision. We have to draw a line somewhere and say, on this side, I don't care what the neuron output is, and on this side, yeah, I'm interested and I want to keep it, right? So this is the basic construct. Very simple, very easy to implement, but by itself, a neuron doesn't do much. Of course, you need to combine them to build layers and to build neural networks. Okay, so here's a very basic example. We have inputs on the left, outputs on the right, and in the middle, we have what we call a hidden layer. And as you can see, it's fully connected to the inputs and outputs. Okay, so this is probably the simplest neural network you could build. So how does that work? How do we train that kind of network with our data? So we're going to build our data set. So that data set is going to be made of samples. So each line in that matrix is a sample, okay? And as you can see, it has as many columns as we have neurons on the input layer, okay? So here we have M samples, and each sample has L features, which is, once again, the number of neurons on the input layer, okay? In a similar fashion, for each sample, we will have a label, okay? Let's say here we're trying to build a classification system, okay? We're trying to classify those samples in a number of categories. Okay, so for each sample, I've got a category, okay? So for that first line here, well, I've got that Y1 value, which is my label, okay? Imagine we have image categories, you know, we have 100 different categories, category 1, 2, 3, etc. Okay, so these are the values that we would use here. Okay, so I've got M samples, so I've got M labels, and I've got, as you can see on the right-hand side, on the output layer, I've got N2 output neurons, so N2 possible categories, okay? And actually, I'm not going to use those values. I don't care so much that it's category 5 or 6 or 62, because it's not really practical. What I want on this output layer, I want the probability in each neuron that a given sample belongs to that category, okay? So for example, for this first sample here, okay, I know it belongs to category, so let's say this is category 0, 1, 2, so I know it's category 2, so the probability that this sample belongs to category 2 is 100%, right? So it's 1. Okay, so this technique is called one-hot encoding. And it delivers good results. So that's what we use when we do classification. So let's put this thing in practice. So here I've got my first sample, and I've got the one hot encoded category for that sample. So actually, you got to rotate that in your mind, right? You got to put that sample on the input layer. You got to put that one hot encoded category on the output layer, okay? And what we're trying to do here is to build a network that can predict this correctly. So whenever we show that X1 sample on the input layer, this is the result that we want to get. Same thing for X2, same thing for X3, etc., etc., etc. Okay, this is the goal of training. Okay, and we're going to measure training by accuracy. So we're going to run our data set through the network, measure the number of correct predictions, and calculate accuracy. Okay? So in a nutshell, this is what we're trying to do. Show some samples, get the correct results. But obviously, initially, the network is blank. It doesn't know what to predict, right? So when I put my sample on the input layer, it's going to output something that's probably completely wrong, like here, okay? So when I apply the network to my X1 sample, I get Y prime, which is completely wrong, okay? So, and that's a problem, because I want to predict the correct results, obviously. So I'm going to use a loss function, which is a mathematical function that calculates the difference between the predicted value and the real value, okay? And there are many different loss functions. I'm not going into details here, right? So just compute the error between what I get and what I would like to get. So I can extend this to a batch of samples, because actually we're not training the network sample by sample. We do that batch by batch to speed things up. So let's say 32 samples at a time or 64 samples at a time. And so I will add up all the error for those samples, and that gives me the error for the batch. Okay? So I'm going to run, let's say, 32 samples, add up all the errors, and this is my error for my batch. Okay? And once again, the purpose of training is to minimize this error, because if I minimize the error, my predicted result gets closer to the actual result, which is what I want. Okay? And how do I minimize the error? Well, I get to tweak all the weights, right? If you're old enough to remember analog TV, is anyone here old enough to remember that? All right, thank you. You remember when you had to tweak that, right? When you bought that analog TV and you go back home and you plug it and it's all fuzzy, and you have to tweak all those tiny things and to get that picture, and it's like, oh, a little bit to the left, oh, a little bit to the right, until you get that picture that is kind of okay. Remember that? It's exactly what we're doing here, right? Except it's not just a few, it's not one knob or one whatever per channel. It's hundreds of thousands, possibly millions, okay? So you're not going to do that manually. So the training process is all about this. You take a batch, you push it through the network, you compute the error, and you run an algorithm called backpropagation, which is going to go back through the network and tweak the weights to reduce error. Just a little bit, right? We won't get it right, obviously, after one batch, but at least we go one step in the right direction, okay? And then we do the second batch and backpropagate again. And we do this batch by batch until we've gone through the whole data set. And this is called an epoch. You may have heard this one, okay? And we're going to run this again and again for 20 epochs, 50 epochs, 200 epochs, maybe more, until we get to a very tiny error, okay? And once we're done, we get a trained network. The weights have been tweaked to minimize error for that data set, all right? The important parameters here, and they're called hyperparameters, are the batch size, the learning rate. So how do you adjust, right? Remember the analog TV, do you go a little bit and then watch and say, okay, no, just a little bit? Or do you go and take big steps, right? So this is an important parameter. We like to go slowly, right? Make sure we optimize slowly. And the number of epochs, how many times do we go, how many times do we push the full data set through the network? Okay, makes sense? Still with me? right? Need coffee? I do. All right. Now, that's the training part. Now, as we will see in a minute, training is actually easy because the network is going to learn that data set, right? It's going to learn it very well. The problem is, how does the network behave when we show it samples that it has never seen before, samples that have not been used for training, okay? That's called the validation data set. If you guys have been doing machine learning, traditional machine learning, you're familiar with this, okay? We kind of split the data set between the training part and the validation part, okay? So we take the validation data set, we push it through the network, and we measure performance. And we like to do that at the end of each epoch, and you will see why in a minute, okay? And we save the model after each epoch, okay? So after each epoch, we have this measure of how well does my network predict samples that it has not seen before, okay? So the question is, when do we stop, right? Do we stop after, how do we know when to stop? Well, if you plot those values, this is what you're going to see. So training accuracy is going to go up, you know, it's going to move up and down a bit, but eventually you get to 100%. It's not if, it's sure. You will get to 100%, right? As I will show you in a minute. If you give it enough time and enough data, I guarantee you get to 100%. Okay? That's the magic of neural networks. They're able to learn anything. If you plot the loss function, well, it will go down to 0, right? And if you plot validation accuracy, you'll see something like this. You know, it will follow training accuracy, and at some point, it goes down. And that's bad, okay? Because then it means you're at this point, your network is not working very well with samples that it has not seen. So of course you want to stop at this point, okay? But when you train, obviously you don't know when to stop, and that's why it's important to save the model after each epoch, so that when you look at those graphs later on, you could say, okay, actually the best epoch, the best checkpoint is epoch 156, right? And after that, it just goes down, okay? And once it goes down, we call this overfitting, which means we learn the training set too well, and that hurts prediction for new samples. It's called overfitting, very important, okay? So that's why you need to save your model, and you need to keep all the checkpoints to go back once training is complete and say, okay, this is the best one, right? Make sense? All right, so let's talk about, that's all you need to know about deep learning, right? See, that was easier, faster, and cheaper than a PhD. So let's talk about MXNet now. So MXNet is an open source library. The project started in 2015. It's a collaboration between industry and universities. And it's the preferred framework at AWS because it does support more languages than most others. It works equally well in cloud environments and in IoT environments. I have some, I run some demos on Raspberry Pis, and it works pretty well. It's part of the Apache project now, so it's you know, it doesn't belong to anybody. It's just driven by Apache, which I like personally. And it's high performance. It's fast. It's faster than other libraries, and it scales very well. You can scale it to hundreds of GPUs almost linearly. So that's very good if you have a huge data set. And actually, it's good timing because MXNet 1.0 was just released yesterday, right? So used to be 0.12.1, and it became 1.0. Okay, so I guess it's stable now. Here are some projects that have been built with MXNet. All these are GitHub projects. You can go and grab them. So object detection, right? Pretty cool. Finding out what's in the picture and where it is, okay? Object segmentation, which is one step further. Find the silhouette, right, of objects, which is kind of important when you do autonomous driving, right? You don't want to know that the old lady is over there somewhere. You want to know exactly where she is, right? 'Cause 10 centimeters are possibly the difference between life and death. So that's, yeah, need to be precise here. You can do text recognition, text detection, even with very, very weird fonts and very bizarre images like this. Again, open source project. You can do face detection, right? So find faces in a picture and find some attributes. Is that a man? Is that a woman? What's the age? Does the person have glasses, etc., etc., right? And we have a service, a similar service called Amazon Recognition that some of you may be familiar with, which is very high level. But if you want to build your own version, there you go. And what about this one, which my personal favorite, it's called pose estimation. And in real time, at about 10, 12 FPS, in this case, you're able to detect the position of the human body and the knees and the shoulders, etc., etc. Imagine what you could do here with video games or I don't know, movies, whatever. Pretty cool thing. And once again, you can just grab that and run it tonight if you want. We can do machine translation. Actually, this one is an open source project by AWS. It's called Sockeye, and you train a model on translating, I don't know, English to French or German to Swedish or whatever. If you have the data set, train it for a few hours and you can translate. Works quite well. So let's look at the key objects in the API, and then we're going to jump into the demo. So the 4 things that you really, really need to build MXNet code are: 1, you need a way to store your data. Remember that X matrix that I showed you, right? Well, that's it. Sometimes it's more complicated than a 2D matrix. It could be multidimensional, so we need an object to store our data. It's called the ND array for n-dimension array. We need a way to build models, right? Define those layers, how they're connected, etc. And that's the symbol API. We need a way to serve data to the model during training. Remember the batches and going back and forth, etc., etc., right? And we're going to use object called iterators. And then we just need a high-level object to basically put the data and the model together and train, right? And that's called module, okay? So these are the 4 objects that we're going to see in the code, okay? So let's jump to demos. Yeah, excited? Yeah, you sound like it, all right. Are you jet lagged too? Okay. So, can you see okay in the back, or is it too small? It's okay, thank you. All right. If it's too small at some point, just wave or yell, or okay. So this is kind of the hello world for MXNet, and as you will see, it's still interesting. Usually hello world is very boring, but I don't think this one is. So here, we're going to create a synthetic data set, right, from random values. 10,000 samples, 8,000 for training, 2,000 for validation, okay? So my matrix has 10,000 lines, right? Each sample has 100 features, okay? So my matrix has 100 columns. My X matrix, 10,000 lines, 100 columns, right? Try to keep this one in your head. And then each sample is labeled with a category that is between 0 and 9, okay? All right, so this is what I'm doing here, just declaring my samples, initializing X and Y, okay? So random values between 0 and 1 for features, and integer values, random integer values between 0 and 9 for labels, okay? So once again, because I know sometimes it doesn't strike you as obvious, each sample is 100 values, right? 100 random values between 0 and 1, float values. And that sample has a label which is an integer between 0 and 9, okay? And I've got 10,000 of those, okay? 8,000 for training, 2,000 for validation. Okay, so once I've built my data set, I've got to split it, like I said, right? And you can see the shapes here, okay? So I will have 8,000 for training, 2,000 for validation, right? Makes sense, I suppose. Now let's build a very simple network, and actually it's very close to the one I showed you, one input layer. one hidden layer with 1024 neurons, and one output layer with 10 neurons. Why 10? Because I've got 10 categories, right? And so each neuron in the output layer is going to store the probability that the sample belongs to this specific category, right? Okay, so it's fairly straightforward defining that network. As you can see, it's 4 lines, right? 5 lines, not a lot of code. Then I'm building my iterator. That's a very friendly object. I give it my data set, and it's automatically going to serve it to the model batch by batch. I don't have to worry about splitting and whatever. Just here's the data set. The batch size is 128, I think. No, it's 16 actually. All right. Okay, 16. So I'm going to serve my samples 16 by 16 to the model. Okay. Now, I've got my model, I've got my data, I need to put both together, so that's called binding. As you can see, just binding the model to the training iterator and the training labels. I'm setting some initial parameters here, setting my optimizer, but that will be used during backpropagation to adjust the weights, okay? And that's it, okay? So let's actually run that one. So here I'm going to learn that data set for 50 epochs. So going through that data set 50 times. Oh, let me try this once again. Yeah, just to reset it. Because here it already learned. Come on, stop. Stop. Okay, let me do that once again. All right. And here we go. So it's very fast, okay, because I'm running on the GPU here, and it's a small data set. So as you can see, very quickly I get to 100% accuracy, right? So it's perfect. I'm able to learn that data set perfectly, even though it's fully random, which sounds weird, right? How could you learn something that's random? Well, we can, right? After 50 epochs, training accuracy is 100%. So we're able to predict absolutely perfectly that data set, okay? And like I said, if you give enough time and enough data to a neural network, it will learn anything perfectly. It's called the universal approximation theorem. If you want to sound fancy tonight, hey, you can use that word. It's not easy to use in a conversation, but you will sound very, very smart, okay? So that's very cool, but remember my curves, right? Training accuracy, it's not a surprise. I knew it was gonna be 100%. What about validation accuracy? So here, I build a validation iterator with my validation data set, and I just run those validation samples through the network, and I score and see what happens there. Well, then accuracy is 10%, which in technical terms sucks, right? It's very, very bad. Okay, actually, why do I get 10%, right? Because I've got 10 classes, so if I'm taking random picks, right, well, over time, you know, my score will be 10%, right? 1 out of 10. So this goes to show, yes, you can learn that stuff perfectly, but when you show new samples, accuracy is terrible, right? Because the data set makes no sense at all, okay? So the lesson here is twofold. First, a network can learn anything. That shouldn't be surprising. 2, if you don't look at validation accuracy, you're not looking at anything, right? So don't get excited when you see training accuracy going up. You need to look at validation as well, all right? Now, let's look at a more meaningful example. Before we go into training stuff, let's pretend we don't want to train, right? Let's pretend we just want to classify images, and we don't have time, and we don't have skills, and we don't have anything to train networks. We want to use existing networks, okay? So those are called pre-trained networks, and you can download them from the MXNet website. And here I've got 3 networks. which have bizarre names, and they've been trained on a large image dataset called ImageNet. Okay, so I've downloaded them already, and these models, like I said, have been trained on ImageNet, which has 1,000 categories, and here's the 10 first categories. So it's animals, plants, and objects. Okay, no humans. So let's try to load those models and run an image through them and see what happens there. Okay, so I'm going to import a few things, and this is how I load a model. It's actually one line of code, right? It's called load checkpoint. Just give it the file that I downloaded from the web, right? It's called the parameter files. It holds basically the weights that have been learned during training. I load that file in memory, and I've got my network ready to go, right? Everything else is just, we'll get back to that. It's just parameters, it's not important. So one line of code, you can load a pre-trained network. Then I have to bind it once again, okay? And in this case, the data that I'm gonna push through the network is one single image, right? And so the shape of that data is one image, 3 channels, because it's a color image, so it's red, green, and blue. And each channel is 224 by 224. Okay, so you can see the shape here is 4 dimensions. What I throw into the network has 4 dimensions. Okay, I need to load the categories in memory, like the one that I showed you, because I want to display them. Then the last thing I need to do is, how do I load an image, a JPEG file, into that 4-dimension array? Well, I'm using OpenCV here. So reading the image, converting it to red, green, and blue, because interestingly, OpenCV uses blue, green, and red, right? Why not? Why not? Then I have to resize the image to 224 to 24, which is what the network, the pre-trained network, knows how to predict. I need to put everything in the right spot, and that's it. Okay, so that's how and that's not MXNet stuff, it's just Python stuff, just to load that JPEG file and build that ND array with 1 times 3 times 224 to 224. Okay, and now I can predict. Okay, so I load my image, turn it into an array, and I push it through the network, right? It's that forward operation. I will get the outputs, okay? And remember I said 1,000 categories, so on the output layer of this model, I will have 1,000 probabilities, 1 for each class. So I don't care about 1,000 probabilities, I just want, let's say, the top 5. So I'm going to sort those probabilities and return the top 5 highest categories for that image, okay? Once again, Python stuff. When it comes to MXNet, it's just one line of code. Okay, so now basically I can just go and maybe I should run those cells. Yep. So here we go. Load that code. Okay. Load my models. Okay, and yeah, I don't care about this one. And now let's predict. So here's my image, right? And as you can see, I'm forwarding that image through 3 networks and printing the top 5 categories. Okay? So the first network, VGG16, tells me there's 96% probability there's a violin in there. ResNet tells me about the same thing, interestingly. And Inception tells me 82%, right? So all 3 do a good job here, right? Because I guess the violin has a very unique shape and it's pretty easy to detect. Okay, it's quite fast here. I'm running on the CPU. It's okay, I guess, less than a microsecond. But now let's try it on the GPU, right? And it's as easy as saying, please do it on the GPU. So I have to load my models again, and you can see the time difference here. Right? We go from 0.63 microseconds to 0.03, right? So it's about 20 times faster. Okay, and if I was forwarding multiple images, like 16 images at a time or something, then it would be even faster. okay? Because those GPU cores, in those GPUs, you have about 5,000 cores that can work in parallel. So you can push a lot of images in parallel and get everything done very, very fast. So that's why GPUs are unbeatable here, okay? So here's an example of using pre-trained networks. And you can see it's fairly easy. Just download a model, load it, push a sample through it, get results, okay? That's literally, I don't know, 50 lines of Python or something. You don't need to write a lot of code, okay? All right, let's move on. So let's train from scratch now. So here I'm working with a data set called MNIST. You're probably familiar with it. It's a data set of 60,000 handwritten digits from 0 to 9. And of course, the game is to learn how to recognize the zeros and the 1 and the 2s, etc., etc. Okay, so I've downloaded the data set already. So let's just run all and see what happens, okay? While it's running, so as you can see, it's always the same thing. I build my iterators, and in this case, I've got a pre-built iterator for MNIST, so it's very cool. This is my network, right? So again, stacking up layers, fully connected, right? This time I've got 2 hidden layers, 512 and 256 neurons. Binding, setting parameters, etc. And training. And here I am training for how many epochs? 50. And yeah, we should be done. And we get to, so I'm saving the model like I said, and I measure accuracy, and I get to 98.43%. So is that good, bad? I don't know. Let's try and predict. So here I've got a similar example like the one I showed you before. I'm going to load my model, okay? And I'm going to predict some real life samples. So these digits I actually drew myself with paintbrush. So those are real, and I'm gonna run them through and see what happens here. So let's just do that. Or I could just go and do this. Okay, so for each digit, I get 10 probabilities, right? So for example, 0 is pretty good, right? 0 is a 0. 1 is clearly a 1. 2 is okay. 3 is very good, right? 4, 5, 6, 7, 8. 9 is completely wrong, right? Because the highest probability is 1, 2, 3, 4. Actually, it thinks this is a 4, because that's the highest probability here. So that's disappointing, right? Because this network was supposed to be 98%, and you know it should be better than that. So let's try another model, and this time I'm not going to use a fully connected model. I'm going to use a convolutional neural network model, yeah, which are really good at, and let's run this one, which are really good at understanding pictures, okay? So here I'm training for 25 epochs, and once again, I'm building the iterator, building the network, binding, training. So you can see, you know, it's always the same steps. And then at the end, obviously I will save and predict. Oops. All right, 20, almost done. Whoa, what's that? So let's see where we get. Okay, we get to 99.12, which sounds better. So now let's repredict. Just need to use the new one here. And yeah, just run that again. And now, lots of ones. And the 9 is a 9, right? Because that model is much better at understanding images, right? CNNs are what you use when you want to do image recognition. Okay, so as you can see, accuracy, it's an interesting data point, but you could say 98.4 or 99.1. There's not a huge difference, okay? But there is actually, right? It really matters, okay? Okay, just to, I don't know how much time I've got left. Not a lot, I suppose. 5 minutes, 4 minutes. Okay, more than enough. Thank you. For the last 4 minutes, I want to talk about SageMaker. So actually, all those notebooks that you saw there, they are running in the cloud on a GPU instance that I created with this new service called Amazon SageMaker, right? Launched again at reInvent a few days ago. So as you can see with this fantastic picture here, SageMaker lets you go end to end, right? So you can run your notebooks like I did. You can actually train models. You can start instances that are going to train models, and you could do distributed training if you wanted to, if you had very large models. You can host, you can save the models inside SageMaker, right? And which I think is great, you can host the models. So you can deploy your models behind an endpoint, a REST endpoint that you can invoke from HTTP or from our APIs, okay? So you can go from experimentation to training to deployment with the same set of tools, right? And here's an example here. I'm not going to run it because it takes a while, but again, it's training MNIST, right? Learning MNIST. And it's very similar to what we did, okay? As you can see, I'm providing my training script for MNIST. Okay, so I build a fully connected network, and I build my iterators, blah, blah, blah. So it's almost identical to the one version that I showed you a minute ago. But the difference here is, in my previous example, I trained locally on my notebook instance, okay? Now, imagine this is a large data set and I need to start 10 instances to train, okay? I can do it with this single code, right? Just this. So this really says, I want to start MXNet training, okay? So I've got this MXNet object. I pass the training script as a parameter. I pass the number of instances that I want as a parameter, instance type, and possibly some parameters for the training itself. And that's it. And this creates a training job, okay? And so this is going to run on 1, 2, 3, 5 instances, depending on what I did, okay? And then I can deploy it, okay? So once again, with that single line of code, the model that I trained gets deployed to another instance, okay? So that instance is going to host the model, and I can now invoke it, right? So I can invoke it from my SDK here, but once again, it's a REST endpoint, so I could invoke it from, you could invoke it from your own application. Okay, so let's give it a try. Here I can, let's see if this is correct. So I'm drawing a digit here. I'm calling predict. Okay, so I'm invoking the endpoint for that model. And yes, my 3 is a 3, right? Okay, so again, here I'm using the SageMaker API to invoke the model, but this is really a REST endpoint that could be invoked from anywhere. You don't need to manage the infrastructure, you don't need to do anything, just deploy it and you're done. Okay, so I think this is really, really cool. And you can see all of that stuff here. Okay, you can see the training jobs, you can see the models that you saved, you can see the endpoints, etc., etc. And you could do A/B testing. So behind one endpoint, you could have multiple models. If you train the same model with, let's say, different learning rates or different parameters, you could have all 3 versions behind the same endpoint and do A/B testing to see what's going on. All right? So Amazon SageMaker. All right, I'm done with the demos. Just want to point out a couple of things here. Okay, so if you want to get started, if you want to get started on all of this, these are the right pages to look at. Specifically, the MXNet website, and of course the repo on GitHub. There's another API in GitHub called Gluon, which is even simpler than the one I showed you. The Sockeye project, if you want to do automated translation. I recorded a video here, which is an overview of SageMaker. It's a 30-minute walkthrough, so going into a whole lot of details on SageMaker and how to use it. So that might be interesting to you guys. And last but not least, this is my blog on Medium, where I regularly post a lot of MXNet content and deep learning content. So if you're interested in this, feel free to read that. Okay. I want to thank you very much for listening. Thank you very much to Code Europe for this fantastic event. It's my first time here. Very impressed. And well, if you have questions, I'll be outside and I'll do my best to answer them. And jet lag was not such a problem after all. So thank you very much. Have a good day.